Hello guys and welcome back. In this video I wanted to explain the technique that I use to add edge displacement to the geometry. Now this workflow or this task has been done in various different ways, and a lot of them are done at render time using so that you don't have to have a high-res geometry in the scene. I personally don't prefer to do it at render time because it's limited to the render, so each render you have to have a specific workflow for that, and a lot of time the main complication for this is to not displace the geometry but to restore the UV coordinate or any attributes that were affected by that displacement. And the resolution for this problem requires, in many cases, the original geometry to be provided, or a point cloud, or some way to restore this. There is ways to apply the inverse displacement, so you can use that to do lookups on the geometry based on a different position. And again, this is a feature that is not available in pretty much any render except Mantra. So if we with the technique that I have, it's very stable, and with the geometry heaviness, it's not that big of a deal. Nowadays, we can have a very high-res geometry and still be able to render that very, very efficiently. So the way it works, I have here a box and a few points. So I'm going to use a Voronoi fracture. And the visualization works by clicking here, so you can see the pieces. And what I'm going to do is I'm going to remesh this geometry. I'm going to add more resolution to it. Now with this remesh, it's going to deform or lose the edges because of the way the tessellation works. And what I want to do is I want to preserve all the look and the silhouette of this geometry. So I'm going to use a group node, and on the original geometry I'm going to set it to edges, call this edges. And in the remesh node hard edges group, I'm going to paste that. As you can see now, it kept everything intact. It didn't change those guys. And there is many ways that we can analyze the geometry to find what the hard edges are and preserve those. And the next thing I'm going to do is I'm going to add a wrangle node and store the position of the points in an attribute called rest. We can call this anything we want. Let's call it original position. Okay, and then if we take a look, it works. It's still pretty fast and the resolution is high as well. And the main thing that I'm not going to use, the main reason I don't prefer to use the RBD fracture node or the Boolean fracturing techniques is that it's not stable. Most of the time it's not going to work with high-res geometry, and it's much slower. So this technique is rock solid. It's going to work. I know that for sure. And if you get any issues, it's probably there's something really wrong with the mesh that can easily be fixed. So what I'm going to do now is I'm going to add a point bob and deform this geometry before doing the fracturing. So let's dive here and do a noise. Let's add a node, add node, and I'm gonna make a floating copy of this. And let's go up. And let's increase the resolution, the frequency. And if we take a look now, you see everything works. It's still pretty fast. And what I'm going to do next is I'm going to restore the position of the original points after we did the fracturing. So we stored that in an attribute called original position. I'm going to say v at p equal v at original position. Pretty simple. And boom, we have edge details. Okay, we can increase the resolution here, and we can increase the frequency and overlay any number of noise patterns or create anything we want. And sometimes it's going to create these kind of issues, but again, we're pushing the noise too much, I think. So we just have to back off a little bit and use more reasonable values. Now that's how the technique is going to work. As for the interior details, we will create our own node for this and our own workflows, so just so you guys can understand this better. But Houdini 17 has a node for this now, so it's called RBT interior details detail, and I'm just gonna connect that in. If you dive inside, I'm gonna lower the resolution to 0.1, maybe even more. Okay, and let's do an exploded view of this. And that's how the pieces looks like. The pattern is still the frequency of the noise is quite high, quite low. So increase that, and that's pretty much it. We have high res geometry. Now, the resolution I used here is a bit high, so I wouldn't be uprising the pieces this much. And I really like the fact that we can have this geometry in the viewport, because we can generate VDBs from this. We can use it to create high-res collision with particles, with pretty much everything we need in the scene. It's not something that we don't see at all. So that's the whole idea of how this is going to work. Now we're going to start implementing trying this on the original geometry, which I have here. Okay, so I have the wall, and I have front wall, bricks, and back wall. And what I'm going to do is I want to try the same technique and see how fast it is to fracture this at a high res. And then we're going to start implementing the recursive technique, where we loop over each one of these guys and fracture them again. And I'll briefly explain it here. So we can do for each name piece. Okay, and I'm going to copy this same guy and use a Voronoi fracture. And now we've done a recursive loop. And what we're going to do is we're going to use the iteration number, which is available here. So iteration, and we're going to read that attribute in the seed. So I'm going to use the expression detail, and I want to read what's the name of the node, the for each node, for each metadata, and then the attribute name is iteration. And I think we need to type in 0 at the end. Yep. And now it's gonna randomize the generation of the points, and we can increase this to 20. Okay. And that number is changing every time. And we can also add 25 to some random number that is generated based on that goes between it goes between 0 and 1, so we need to fit this. So we're gonna fit this guy. I'm gonna use a fit 0 and 1 because I know the random goes between 0 and 1. Okay, and then we're gonna fit it between 1 and 10. I'm just checking for the parentheses. Yeah, this is it. But I guess it's not working. Okay, I think it's working now. It's 26, but I'm not sure if the random is changing. It's hard to tell here. So let's set this to 5. And then that's the idea. That's the whole idea for the fracturing. Let me turn this off and let's turn this on. And I'm gonna call this second. So it has different name. And I guess we can't view this way. And the main thing with this is that we can control a lot of aspects for the secondary fracturing. We can also store the same the point position. So here I can store the original point position and add another noise to it, and this time I'm gonna use a higher frequency and lower amplitude because the piece is smaller. Okay, and then I'm going to restore that afterwards. So let's do this, and this way we can get different types of edge details, not just one type. And I'm going to create a connectivity attribute, and I'm going to generate a color based on that. This will give me an ID number, and I'm going to say based on color, and delete existing. Sorry, it's class attribute. Yeah. Cool. So that's the fracture that we have now. As you can see, we're getting very cool pattern. Obviously, this is with a very uniform point distribution. Okay, we can still work on this and make it look a lot more interesting. And I don't want to spend more time on this because we're going to redo the whole thing, and I want to explore it on the main wall. You can see already the pattern is looking very interesting. And we can run this guy here. And the reason it's not working now is because the name attribute is not set correctly. The exploded node is not working as expected because the name attribute got messed up in some ways. So that's it for this video. Next, we're going to look at this and how we can redo the same thing and apply the remeshing and everything on the geometry so that we get enough edge details in there. Thank you guys for watching, and see you in a bit.